Hello and welcome back to a video series on MAC 1105 College Algebra. My name's Sean Perry. These are guided notes number 20 in the series on chapter 4.5, Rational Functions. Before we begin, we should define what a rational function is. We're going to define a rational function r of x as a quotient of two functions, where p of x and q of x here are polynomials. One of the main things to keep in mind about a rational function is that since we're doing this division, we are going to have to make sure that q of x is never 0. This will form the domain of our rational function. Let's look at some examples to see how this relates to certain geometric features of the graphs of rational functions. Here's a typical looking rational function. Notice that these dotted lines indicate asymptotic behavior, where the graph gets closer and closer to the dotted lines. This dotted line is the line x equals 6, and this is our vertical asymptote. When we see vertical asymptotes in rational functions, the graph never crosses those lines, and it pertains to some place where we divided by 0, that is to say, over a root of the denominator. So these points are removed from the domain. We would say that the domain of this rational function would be all of the points except for 6, which we write in this way using union symbols and open intervals, parentheses. On the other hand, it also has this asymptotic behavior in the horizontal direction at the line y equals 5. The rules about crossing horizontal asymptotes are a bit more lax. Now, this graph does not seem to cross that horizontal line. So we are going to have a restriction in our range. Here we can see that we are going to attain all y values from -infinity up to 5, but there doesn't actually appear to be a point on this graph where it crosses that horizontal line, and so there is no point at which the y value is 5. We sort of have to leave it out. Again, I'll just say that doesn't happen all the time for horizontal asymptotes, the way it does for vertical ones, that it creates this range restriction, but it does appear to do that for this particular graph. The parent function for this particular graph that they've drawn, a prototypical example of a rational function, is the so-called reciprocal function 1 over x. This takes in a number and gives us its reciprocal. It's defined at every point except for, of course, at 0. And as we get closer and closer to 0, our reciprocals become arbitrarily large, either positive or negative, respectively. And as we become very, very large, our reciprocals become very, very tiny, either negative or positive. Tiny numbers, depending on if we are on the left or the right, respectively. So that gives us this general cross kind of shape with these two swoops around its asymptotes. And we can see that behavior reflected here. Another kind of behavior associated with rational functions is this one, where they both seem to swoop in the same direction. This is very similar to the function 1 over x squared. As before, there is an issue around 0, where we might divide by 0, but the idea is that as I square a number less than 1, it becomes yet less than 1, and we're actually going to shoot off towards infinity faster. And we're going to dive down towards this positive x-axis even faster, as x squared becomes very large very quickly. And the negatives, well, their squares are positive. And so we wind up shooting off towards positive infinity as we approach from the left-hand side from the negative numbers as well. As before, we have this vertical asymptote where we would divide by 0, and this has the equation x equals -3. I'll use VA as an abbreviation for vertical asymptote here on out. It is a domain restriction, and so the domain of this function would be from -infinity up to -3, and it would not include it. So we would leave it out this way. Now, the range of this function is abbreviated by this horizontal asymptote. Here we can see that actually it doesn't seem to be going below that at all. So we wind up with something like y equals -1 for our horizontal asymptote, and our range of this function is only numbers greater than that. So, and it doesn't appear to cross it either. So we would have from -1 up to infinity for our utilized y values, aka our range. These are two of the simplest behaviors for rational functions. When we put other more complicated polynomials up top and bottom, we're going to see a wider variety of behavior, including things like crossing the horizontal asymptote, in the intermediate in middle values and wholes, but we'll get to all that in due time. Here are some questions we're asked to find the domain of the given function. And really what we want to see is where is the denominator equal to 0, because we're going to leave those points out. So to leave those points out, let's figure out what those points are. We set it equal to 0, and we find x is equal to 2 will 0 our denominator. Therefore, our domain will be every point except for 2, which we write this way. Okay? Now, moving on, looking at this one, we want to see where is x minus 9 equal to 0. That's, of course, at x equals 9. And so we would exclude this value from our domain, which looks like this in set notation. It's important to be able to find the zeros in our denominator. Where is x squared plus 8x plus 12 equal to 0? We have a variety of methods for figuring out where that is, but let's use factoring here since it factors so easily. These are the locations where it is 0, -6 and -2, so we have to leave those out. Same thing here. What are its zeros? I like to multiply both sides by -1 here to flip my leading coefficient and make this easier for me to factor. Looking for factors of 12 with a sum of 7, that's going to be 4 and 3. And reducing these to get rid of my extra 12, I wind up with the following two factors, which have roots at 1/3 and 1/4. And we would excise those from our domain this way. Here we have something that looks like the sum of two rational functions. Now, is that in fact a rational function as well? The answer is yes. We could in fact write this as a single fraction. It's not necessary for doing this problem, but let's just remark that if I multiplied over here by 10 minus x, and over here on the top and bottom, of course, by x minus 13, what we would wind up with is, now I'm not going to continue to press this forward. What you should note is that the top is a polynomial and the bottom is a polynomial, so this is a rational function. Now, we could also have looked straight away at this original function and said, well, when are either of my denominators going to be 0? Because that will, of course, cause one or the other of these components to be undefined. And we could see in either case that that's going to be where x is equal to 13 or x is equal to 10. And so we leave those out of our domain as such. Here's two fun ones. The equation 49 minus x squared is going to have zeros where x is equal to plus and minus 7, which we could see either by factoring this as a difference of two squares, or by moving the square over and taking plus and minus the square root of both sides. And so our domain of n removes those 2 points as such. Now, on the other hand, 64 plus x squared will be equal to 0 when x squared is equal to minus 64, which happens at x equal to plus and minus 8i. Now, those are complex numbers, and we're talking about what real numbers do I need to restrict. There are no real numbers which make the denominator equal to 0, because these are our only zeros for the denominator, and so there are no domain restrictions. That tells us that the domain of t is the whole real number line. It's sort of a starting assumption that we are working with the real number line as our natural domain. We could also have considered the complex plane as our domain, at which point we would have to excise these from that domain. You still couldn't divide by 0, even if we were using complex numbers. But we are going to deal in this class with real valued rational functions, and we're going to look at their graphs over the xy plane. So in that sense, when we talk about our domain restrictions, we're only going to be talking about what points do I need to remove from the real number line so I'm not dividing by 0. For equations 9 to 11, they want us to find the vertical asymptotes and also determine if there are any holes. They say to determine the x values. Let's actually do one better and determine the xy pair where this hole exists. But first, what is a hole? I think a very important example of a hole can be determined by discussing this question. Is x over x truly equal to 1? And the first reaction is yes, something divided by itself is always 1. But it's not that in every case. We actually have this implicit assumption here. This is true if and only if x is not equal to 0. If x is equal to 0, we have a bit of a problem here. And we can sort of distinguish that problem by graphing these two things. So on the right-hand side, I'm going to graph the line y equals 1. That's just a constant flat line with 0 slope that goes through all the values where y is equal to 1. On the other hand, if I graph the function y is equal to x over x, what I'm going to see is that it's 1 everywhere except for at 0. And at 0, it's not defined. And the way that we talk about that kind of behavior of being equal to some value, but at this single point not being defined, is we call it a hole. And we draw a big circle there to sort of call our attention to the fact that that one point has been missing. Of course, a point isn't that big. This is just a kind of symbol to designate that there is a missing point in the line right there. But we do that so that you can distinguish between these two graphs easily, because they truly are not equal to one another. We're going to say that this is equal when we cancel fractions, right? But the implicit assumption is that we are no longer talking about x equals 0 as being a valid input. It remains outside of the domain to put 0 into this function, even if we canceled. If we would have ever made a rational function have a 0 in the denominator, that point has to get left out, and we leave it out in this way. So this is another kind of behavior that you'll see in addition to vertical asymptotes that might occur when you're dividing by a 0. If you divide by a 0, but it cancels completely, you're going to have a hole at that point. So let's see if we can spot a couple. We're going to be looking for where are we dividing by 0 and where is it canceled, versus where are we dividing by 0 and it is not canceled. Here we have a 0 where x is equal to 6, and there is no corresponding x minus 6 term on top, so that's going to get a vertical asymptote. The next problem, we would like to factor this denominator and get 11x over x times 2 minus x. Here we can see we have two places where the denominator is divided by 0. We're going to have one issue at x equals 0, but there's cancellation that goes on there. This cancellation is complete. There's no other x terms anywhere in the top or in the bottom. And what we're going to wind up with then is a hole. Now, they ask for the x values for these questions. We could also determine the y values pretty quickly. Notice that if we really canceled that thing, we'd get 11 over 2 minus x. And if I plugged in x into this equation, now keep in mind, I'm not saying that point is defined. I'm saying if this was our starting function and I plugged in 0 here, I'd get 11 over 2. Our original function isn't going to be defined at 0, 11 over 2. It's going to have an open circle there. So I'm not saying we get 11 over 2 for this function. I'm saying we get 11 over 2 for this function, where we already had this sort of implied understanding that we weren't going to plug in 2. So this is a little bit of a trick, because no, we're not really plugging in 2 into the original function. That was forbidden. Instead, I'm plugging it into this function after cancellation just to determine what y value is left out of our graph. There will be a hole at 0, 11 over 2. All right, we want to proceed as we did with the last one. First, we factor the denominator. It's a difference of two squares, so I wind up with x minus 12, x plus 12 on the bottom. And if I cancel one of these things, like this, we're going to have a hole at x equals 12. So the remaining fraction looks like 1 over x plus 12. And there was a hole. There was a hole at positive 12. And notice that I plug in positive 12 into this, I get 1 over 24. This would be the y value of my hole. We also have a vertical asymptote where this remaining factor would be equal to 0, which is of course at negative 12. And so we have a vertical asymptote at x equals negative 12. For a horizontal asymptote, we're thinking about a different thing. We're thinking about what's called the long-term behavior of the function. We want to know what happens when x gets really, really big, positively or negatively. And what's going to turn out to be the case is we can pretty much ignore everything except for the biggest terms on the bottom and the top. Let's go over a general rule first. If we take our rational function and expand it so that it looks like ax to the nth power plus smaller powers, where this could even be to the 0 power to give me a constant up front, or we have bx to the m plus smaller powers, then all we need to look at to determine the horizontal asymptotic behavior are these two leading terms. And we actually have just three cases. Either n is greater than m, either n is less than m, or n is equal to m. If n is greater than m, there won't be a horizontal asymptote, And that's because the bottom can't divide by numbers big enough to counteract the top and how big it grows. Now, if on the other hand n is less than m, then the denominator grows faster. And what we will see is eventually the things we're dividing by are astronomically bigger than the things that we are multiplying by in the numerator. Now, if we divide by something much bigger than the thing we're dividing into, we get something very close to 0. And so this will give us a horizontal asymptote with the equation y equals 0. On the other hand, if the two are equal, then they're going to grow in balance with each other. And eventually these terms dominate over the lower order terms, and we get something that's approximately equal to the ratio of their coefficients. So we wind up with a horizontal asymptote at 0 equals a over b. So now let's go ahead and apply that to these problems. As stated, you don't need to worry about what these lower order terms are. You just have to look at the top and the bottom. The top has degree 2, the bottom has degree 1, and 2 is greater than 1. So this tells us that there will be no horizontal asymptote to speak of. For the next one, they've decided to write it out of order. It's no matter. What we're looking for is the largest terms in the top and bottom. Those have been scrambled and put at the ends, but we can see here that we have 4 is the greater of the two. The denominator has the greater value. This is going to tell us that there is a horizontal asymptote at y equals 0, the x-axis. Here, if once we ignore our lower order terms, we have x and x. We have sort of an equal degree on the top and bottom. And that tells us that we are looking at the ratio of the coefficients for our horizontal asymptote. This will be at y equals 4 over 1, which we might as well just write as 4. Again, we've got some scrambling here. We've got the degree of 2 on the top. We have a degree of 2 on the bottom. And that tells us, since 2 is equal to 2, that we're going to have to find our horizontal asymptote by looking at the ratio of their coefficients, 2 to 3. And there we have it. The next question has to deal with graph matching through transformation rules, right? We need to still know our transformation rules, that this corresponds to a right shift of 4, and this corresponds to a up shift of 5. So our parent function is 1 over x, which has this appearance to it. And so we want to take a look at these graphs and find where this particular graph with this orientation has been featured. We haven't flipped it at all, so we're still going to have our graph in the upper right and lower left corners of our asymptotes. It's helpful to just look at the position of where the two asymptotes cross in these graphs to try to see where things have been shifted to. The point we are looking for is one which has been shifted to the right 4 and up 5. Well, this one has been shifted to the right 4 and up 5, but does it have the right orientation? Notice how its graph is in upper left and lower right-hand corners of that cross, while this one is not. So let's keep looking, and we see one where, yes, we've gone right by 4 and up by 5, and we haven't done any of that horizontal or vertical reflection or rotation or whatever. It has the same orientation, the same location of these two lobes of graph, these two components of the graph, as the original parent function. So this is going to be our graph. This one's asking for a little bit more detail. It wants us to write the equation for each one of these rational graphs. We could look at the horizontal asymptote to notice any upshift. We also want to note what has happened to the origin of the original graph, which had its vertical asymptote at 0. This vertical asymptote has been moved to -3, and its horizontal asymptote has been moved to +2. It's also been flipped upside down. So we can tell from that the following things. Our graph has been flipped. The x squared bit has been moved to the left by 3. And outside of that, we know that it has been upshifted by 2, which we add to the end. Same kind of methodology for this one. It's been right shifted by 4 units, it's been upshifted by 4 units, and it has been reflected. I should note we should also be checking to see if it was scaled, but we can see how it seems to leave these boxes of size 1 around there. So we know it hasn't been like vertically stretched or something like that. No, but it has been reflected, it has been right shifted, and it has been upshifted. So we would want to record that this way. These last two haven't been reflected. One has been right shifted by 4 units and upshifted by 1, which we would write like this. The other one has been downshifted by 1 unit and right shifted by 1 unit, which we would write like this. Okay, that'll do it for these. I should probably note that we could have applied this same kind of process to these to figure out what their equations are. Here are those equations if you are interested. Here we have some more matching games that they want us to play. This function has gone down 1 and to the left by 3. That would be here. This one has gone down 5 and to the left by 5 and been flipped. That would be here. This one has gone up by 5, left by 2 and been flipped. That's right here. This one has gone up by 3 and right by 4, and it has the same orientation as the original one, so that would be here. And there we go. Okay, here we have some more. We really just want to take a look at what happened to that crossing point of the vertical and horizontal asymptotes. That's going to tell us our transformation from 0. And we want to look at whether or not it has the same orientation as the original one, or whether it has a flipped orientation from the original one, which is 1 over x. So this might be 1 over x, and this might be minus 1 over x. So this one has the same orientation. It's been right shifted by 3. It's been up shifted by 2. This one has the same orientation. It's been left shifted by 5. It's been down shifted by 5. This one has a flipped orientation. It's been left shifted by minus 1, and it's been up shifted by 5. This one has a flipped orientation. It's been left shifted by 2. It's been down shifted by 4. All right, for the following questions, we are going to completely analyze the rational function given. We're going to want to find all of the following properties: the domain, the vertical asymptotes, holes in the graph, asymptotes in the graph, and the intercepts of the function. And then we're going to pick some additional points that aren't any of the ones previously discussed and use these to graph the function in question. If we follow all of these guidelines of geometry assiduously, we can get a usually pretty good sketch of what the function looks like, but we can also confirm the sketch of our graph using a graphing utility. So for our domain of f, we want to look out for the places where minus 4x plus 8 is going to be equal to 0. Minusing 8 and dividing by minus 4, we get x is equal to 2. So our domain must exclude those values, and we go from negative infinity up to 2. We exclude it. We go from 2 up to infinity. This 0 in the denominator is not canceled, and so we're going to wind up with a vertical asymptote at 2, which has the equation of lie x equals 2. We didn't find any holes because there was no cancellation of factors from the numerator and denominator. The horizontal asymptote, will both of these match? So we're going to want a horizontal asymptote at the ratio of their coefficients, which is going to be 5 over minus 4, or negative 5/4, as you like it. Our y-intercept is going to be the value of f where x is equal to 0. Now, plugging that in, we find a numerator being equal to 0, which gives me 0. This is going to tell me something about the x-intercepts too. The x-intercepts are going to be where f of x is itself equal to 0. But what we should keep in mind when dealing with rational functions is only the numerator can control where the zeros are going to be. If I multiply both sides by negative 4x plus 8, I wind up with 5x equals 0, which is going to again give me a 0 at x equals 0. And so we wind up with an x and y intercept, that is to say, an intercept at the origin. So now let's start to sketch this. We know x is 2, we have a vertical asymptote. We know at negative 5 over 4, we're going to have a horizontal asymptote. Let's pick a few more points to evaluate. So plotting these points, we start to get a reasonable picture about what this is going to look like. We cannot cross the vertical asymptote. We're going to wind up running through these points and then running adjacent to it and swooping off towards infinity. Then on this side, clearly we split along the asymptote and come back this way, and then we're going to come up to the horizontal asymptote and have to hug that. The same thing is going to happen on this side as such. And there's our graph. So here's another. Let's begin with the domain. We would like to know, first off, where is x minus 1 equal to 0? And that'll be at x is equal to plus and minus 1. So these points must be xized from the domain of f, which we can do with the following symbols. Now, what are the vertical asymptotes? What are the holes? Well, notice that neither one of these factors, x plus 1 or x minus 1 has a corresponding factor up top. So both of those are going to relate to vertical asymptotes. We will have vertical asymptotes y at x equals minus 1 and x equals positive 1. There are still no holes because there's no cancellation that happened. We take a look at the degrees of the numerator and denominator. Here I have degree 1, here I have degree 2, and that's going to tell me that there is a horizontal asymptote at y equals 0. If the degree of the denominator is larger, then the horizontal asymptote will be at y equals 0. Likewise, we could check our x and y intercepts. Let's check our y-intercept first. That's going to be, where is f of 0, and we can see just by plugging in a 0 here, which is not a forbidden value, that we wind up with, again, a 0 at 0. This is going to show up when we go to look at our x-intercepts, which is where is f of x equal to 0. And again, the numerator alone controls the zeros of the rational function. If I multiply on both sides by the denominator, I just get the numerator set equal to 0, which happens at 0. So we found our x-intercept. Again, it's the same as our y-intercept because it's at the origin. Now we had vertical asymptotes at plus and minus 1. And here I would just like to call our attention to the behavior of either being in the same direction of the asymptote. It has to do with whether or not the multiplicity of the 0 in the denominator is odd or even. In the same way that crossing a 0 had to do with whether the multiplicity was odd or bouncing off of it if it was even. So one of the things we can do pretty nicely then is looking at these zeros of the numerator. I'm going to cross at this one because it has a odd multiplicity. It's to the power 1. And likewise with these asymptotes, I'm going to flip around those asymptotes. I'm going to have the splitting kind of asymptote rather than the same directional kind of asymptote, because those have multiplicity 1 themselves. So let's pick some more values to plot. So let's plot those points. At minus 2, I'm at minus 4/3. We know that this thing is going to ride along this asymptote and then swoop down to hug this one here. We know it splits along that asymptote, and we could confirm that by noting that it goes through 4/3 at a half, which is right here. So we have something which looks like this. Now it's going to go through the point 0, 0, and this is why I was saying before that you're absolutely allowed to cross the horizontal asymptote in the middle of the graph. And then it shoots down towards this asymptote here, passing, of course, through negative 4/3, and then through positive 4/3 at 2. It's going to come back in from up top and then hug along this axis here. And it will never cross it again because we know there are no other x-intercepts besides this one over here. All right, so the domain of f is going to be all the places where this denominator cannot be 0. And minus 4 plus x squared is equal to 0 when x is equal to plus and minus 2. So we remove those points from the domain this way. And we note that the only factors up top here are this 2x squared. So none of these divisions by 0 will cancel. We're going to have vertical asymptotes at each one of those points. So we'll have a vertical asymptote at x equals minus 2, and we'll have a vertical asymptote at x equals positive 2. Just mark those on the graph right now. What about holes? There are no holes because there's no cancellation. What about our horizontal asymptote? Well, we take a look at the degrees. The degrees match, so we are going to have a horizontal asymptote. It's going to match at the ratio of their two coefficients, which is going to be 2/1 or just 2. Now let's consider our x and y intercepts. So our y-intercepts are going to be where f is equal to 0, and plugging in 0, we get a 0 here. For our x-intercepts, we have to solve for when is f of x equal to 0, but that's only going to happen when the numerator is equal to 0, if there's not a hole there. If we multiply both sides by the denominator, we just get 0 equals to 2x squared, which is going to have a 0 at 0. Now, if we were to have factored this denominator, we do have a difference of squares here. We could have rewritten this as x squared over x minus 2, x plus 2. These have multiplicity 1. This 0 has multiplicity 2. And so we know something about the crossing behavior just from those. We can also plot some points to sort of help us figure this out. Let's put in minus 3, minus 1, 1, and 3. We could be using a calculator to check our work and speed this along. I'm going to put 2x squared in the numerator, and I'm going to put minus 4 plus x squared in the denominator. From the table, we could actually just read off the values to complete this chart. Plotting those points, we kind of get a sense of what's going on with the asymptotes, and we could also use the fact that these are multiplicity 1 to note that this is going to split around this, giving me part of it that goes up and part of it that goes down towards negative infinity. This multiplicity 0 at 0 is 2. It's an even multiplicity 0 at the origin, and so it's going to bounce off of it, which we could see by our test points as well. This then shoots down towards negative infinity, splits, and comes back from this direction to intersect this point, and continues on, which we can confirm the general shape of using our graphing utility. To proceed with analyzing this next one, I would first factor the denominator. It's a good idea to just factor everything at the beginning of these so we can see where the zeros of the denominator are and if there's any corresponding factors up top. We want factors of 18 with a difference of 7, which are 9 and 2. And this tells us that our domain must exclude the two values which would zero this out. This means that we're going to have to remove the points minus 2 and the point 9 from our domain so that we avoid putting zeros in the denominator. And that'll give us vertical asymptotes at negative 2 and 9. There are no holes because there's no cancellation. We note that the degree of the denominator is larger than the degree of the numerator, so we have a horizontal asymptote at y equals 0. Plugging in 0, we can find our y-intercept. Setting it equal to 0 and solving, by multiplying the denominator away, we find a contradiction. There are no values at which this is true, and so there is no solution and hence no x-intercepts. I'm going to put that function into our graphing utility so that I can use the table to find some values quickly to plot. We notice the error that we get if we plug in something at the values which are not in the domain. I know the fractions that go along with all of these values except for this last one at 2, so let's just plug in a 2 here and see what we get. We'd wind up with minus 8 over 2 minus 9 is minus 7 times 2 plus 2 is 4. This part would reduce, and we would get ourselves 2/7. Now, our behavior is going to be split around these asymptotes, and we're going to have no x-intercepts. Let's also get our vertical asymptotes in the right place. This is positive 9, negative 2. Really, what these are supposed to let us know is that it changes sign here, and that also it does not touch the x-axis. It's only going to become very small here, but it's going to then reverse direction without ever touching it and bounce off and head up this one. We know that because it has no x-intercepts, and so it cannot touch the x-axis. It's going to get kind of corralled in this way, and then it's going to scoot back down and flip around that asymptote as well, which we can verify by looking at this graph. Alrighty, that's going to do it for this video. Thank you very much for your patience, and have a great day. Good luck with your studies. I'll see you in the next one.